Hello students, welcome to my channel Arun's Physics Portal. In this lecture, I will be talking about Butterworth's second order low pass filter. This topic is meant for MSc Physics and Electronics students and also for BE and BTech students of EEE and EC branches. The JRF and NET aspirants will also find this topic useful. The complete note of the topic is given here for your convenience. I hope you enjoy going through it. Now let us come to the topic. Figure 1 shows you the Butterworth second order low pass filter. In the first order low pass filter, we had one resistor and a capacitor connected like this. Okay. In the second order filter, we have two resistors and two capacitors. If we have three resistors and three capacitors connected like this, that will be a third order low pass filter. If you break up the circuit, it will be easier for you to remember the circuit diagram of the Butterworth second order low pass filter. The circuit enclosed in the red line is your non-inverting amplifier whose output V0 is equal to 1 plus Rf by R into Vq, and not this is the output of this circuit and not 1 plus Rf upon R into Vi, where Vi is the applied potential here. This is because whatever potential you apply to the circuit does not reach at the input of the non-inverting input of the op amp. So a part of the potential applied drops across these resistors, and only a small part of the applied potential Vi appears at the point Q. The potential at the point Q, we call it Vq, and the potential at the point P, we call it as Vp. Okay, so you have to find out the value of Vq, the potential at the point Q. So this will be known only if P is known, potential at the point P is known, and the potential at the point P will be known only if you can find its value in terms of Vi. So finally, what we will get? We will get the value of Vq in terms of Vi. So note this. So this part is your non-inverting amplifier. This circuit diagram include within the purple line is your Butterworth's first order low pass filter, and we have added one more RC network. Then this becomes your Butterworth's second order low pass filter. Okay, so what you have to do? You have to simply find the value of potential at the point Q in terms of potential applied Vi. So let us see how this can be done. Okay, you apply the voltage divider rule. You apply the potential here Vi, and the current I1 flows through R1. At the point P, this current is divided into two parts. One part I2 goes through C1. Another part goes through R2. At the junction point Q, this current I3 may be divided in two parts. One part will go into the non-inverting input of the op amp, other will pass through C2. But because the input impedance of an op amp is theoretically infinite, practically no current will enter into the non-inverting input of the op amp. So all the current that passes through R2 will pass through C2. Okay, so that we have I1 equal to I2 plus I3. All the current that passes through R2 will flow through C2. Okay, so apply the voltage divider rule. If you apply the voltage divider rule, you get the value of Vq as Vp upon 1 plus S R2 C2, or Vp equal to 1 plus S R2 C2 into Vq. Now apply Kirchhoff's current law at the point P. What do you get? You get I1 is I2 plus I3. Now apply Ohm's law to find the value of current. So this is I1 is V1 minus Vp upon R1. I2 is the current that flows through the capacitor C1. So this is Vp minus V0 upon 1 minus 1 upon SC1 plus I3 is the current that flows through R2. So this is Vp minus Vq upon R2. Okay, you simply simplify this equation and get this result. Even though this is a lengthy process, I have done it for your convenience. Now in this equation, you simply put the value of Vp. Okay, so you get this equation. So we have this equation now containing only Vq. So you can find the value of Vq from this equation. So Vq comes out to be in terms of V0 and Vi. Okay, now the output V0 is given by V0 is 1 plus Rf upon R dash into Vq. Note that V0 is not equal to 1 plus Rf upon R dash into Vi, because Vi is the input signal, but the signal that reaches the non-inverting input of the op-amp is Vq, and therefore V0 has to be equal to 1 plus Rf upon R dash into Vq. Okay, so I write 1 plus Rf upon R dash equal to Af. So Af is equal to 1 plus Rf upon R dash. So put the value of Vq here from equation 2. So this is Af into R2 Vi plus S C1 R1 R2 V0 upon 1 plus S R2 C2 into R2 plus S C1 R1 R2 plus R1 minus R1. So you keep all the terms containing V0 on one side and other terms containing Vi on the other side. So what do you get? You get this expression. Simply mathematical manipulation and nothing else. See here, V0 is here and V0 is also here. So you have to transfer this term, this upon this on the left side. So this is exactly what we have done here. V0 into, this is 1 minus Af into SC1 R1 R2 V0 upon 1 plus S R2 C2 into R2 plus SC1 R1 R2 plus R1 minus R1. Okay, by simply manipulating the terms and rearranging them, we have this equation. So that we have on the left side only V0, on the right side we have Vi. Okay, so now V0 into this. What we have done here? We have expanded this term. We have taken the product and expanded it. So this is all. On the right side we have Af into R2 into Vi. So V0 upon Vi is Af into R2 upon this term. This is written here. So now divide both the numerator and denominator by R2. So what do you get? We get V0 upon Vi is Af upon this term. The same that is written here. What is the difference? Difference nothing. So V0 upon Vi is simply equal to this term, where we have taken is common here, and all the terms having a factor S is written within this enclosure. So I divide both the numerator and denominator by R1, R2, C1, C2. So on the numerator we have AF upon R1, R2, C1, C2. Okay, in the denominator, if you divide this term, first term, by R1, R2, C1, C2, this goes and we have simply S square. This term doesn't contain a factor R1, R2, C1, C2. So we have divided by R1, R2, C1, C2. The last term 1 we have divided by R1, R2, C1 and C2. Okay. Now the standard transfer function for the second order Butterworth filter is given by expression 4. V naught upon Vi is AF into omega n square upon S square plus alpha omega n plus omega n square. This is equation 4. Now you compare equation 3 and 4. In both equation 3 and 4, on the left side we have V naught upon Vi. Now, in the numerator, we have AF upon R1, R2, C1, C2 in equation 3. And equation 4, we have AF into omega n square. So, AF is common in both of them, and therefore, omega n square has to be equal to 1 upon R1, R2, C1, C2. Moreover, see here, in equation 3, we have S square. So, this is here S square. The coefficient of S here is this factor, and the coefficient of S here is alpha omega n, and therefore this term from here to here must be alpha omega n. Okay, and then this is a constant term. This term is a constant if R1, R2, C1, C2 are constant. So this is a constant term. So this is your this term. So if you compare equation 3 and 4, what do you get? You get omega n equal to 1 upon root over R1, R2, C1, C2. And this is nothing but upper cutoff frequency denoted by omega h. Okay, omega n square is here and this is here. The term containing S square is this. Here, this is this one. The coefficient of S here is alpha omega n. Here it is this term. So we have alpha omega n is nothing but alpha omega h, because omega n is now omega h. So put the value here. This is R1 C1 plus R1 C2 plus R1 C1 into 1 minus AF upon R1 C1 R2 C2. Now let us take R1 equal to R2 equal to R and C1 equal to C2 equal to C. Then what happens? Then we have omega n is 1 upon root over R into C into C. So this is 1 upon R square C square root over. So this is 1 upon RC. And this is what we have written here. Okay. Now alpha omega h, when R1, R2 are equal, each being equal to R, and C1, C2 are equal, each being equal to C, then this factor becomes 2RC. RC plus RC is 2RC plus RC into 1 minus AF. So this is written here. This is 2RC plus RC into 1 minus AF upon this is your R square C square. Okay. Now see, we have seen that omega h is equal to 1 upon RC. Okay. So 1 omega h cancels with RC. Okay. The numerator we have RC in the first term and in the second term also. So these RC cancel with these RC. So what is left out here? This is 2 plus 1 minus AF. So this is 3 minus AF. So alpha comes out to be 3 minus AF because omega h is 1 upon RC. For the Butterworth second order low pass filter, alpha is root over T, and therefore the preceding equation gives you, we have alpha equal to root over 2. Let me write it here. Alpha is root over 2. This is 1.414. This is 3 minus AF, or AF is 3 minus 1.414. This is 1.586. and therefore 1 plus Rf upon R dash is 1.586, or Rf upon R dash is 1.586 minus 1, and this is equal to 0.586, and therefore Rf is 0.586 into R dash. So this equation 7 can be used to get maximally flat frequency response. How to find out the gain? So we make use of the standard transfer function for the Butterworth second order low pass filter, and we write again V naught upon Vi is AF into omega h square upon S square plus S alpha omega h plus omega h square. You divide both numerator and denominator by omega h. So here we get omega V naught upon Vi is AF upon S upon omega h whole square plus S upon omega h square into alpha omega h plus 1. Okay, so this one is written here. This is omega h here, and this omega h square. So this one cancels with this one. Okay, so you get here S upon omega h into alpha plus S upon omega h whole square is here. So we have finally V naught upon Vi is AF upon 1 plus, we have S equal to j omega. So this is j omega alpha upon omega h plus j omega by omega h whole square. So this is equal to AF upon 1 plus j alpha F upon Fh minus F upon Fh whole square, because we have omega is equal to 2 pi f. Okay, so we have V naught upon Vi is AF upon 1 minus F upon Fh whole square. This term and this term is real, this is imaginary, plus j alpha F upon Fh. So the mod of this will be AV equal to V naught upon Vi. Mod of this is AF divided by root over 1 minus F upon Fh whole square to the whole square plus root over 2 F upon Fh whole square. Because you know that if we have x equal to a plus jb, then mod of x is nothing but square of the real term, square of the imaginary term, and then square root of this. So this has been used here. Okay, so we have AV equal to AF. This is a minus b whole square. This is 1 plus f upon fh to the power 4 minus 2 f upon fh square plus 2 f upon fh whole square. So this term cancels with this term. Okay, so we are left with AV equal to AF upon root over 1 plus f upon fh to the power 4. In general, we have AV is equal to AF upon root over 1 plus f upon fh to the power 2n. For the first order low pass filter, n equal to 1. For the second order low pass filter, n equal to 2. For the third order low pass filter, n equal to 3 and so on. लेकिन जैसे हम जाते हैं towards higher order filters, the analysis becomes more and more complex. And also above the second order filter, the system becomes unstable. And therefore, to maintain the stability of the circuit, we mostly confine ourselves only up to the second order filters. So from equation 9, the following conclusions may be drawn. When f equal to 0, f upon f naught h is 0, which gives you AF, V equal to AF. So gain is maximum here at frequency 0. As f increases, f upon fh increases, and so AV decreases. It follows from equation 9. Okay, at f equal to fh, AV is AF upon root over 2. And when f tends to infinity, AV tends to 0. Let us see how it takes place. AV is AF upon 1 plus F upon FH to the power 4 root over. When F and FH are equal, this is 1, so this is 1 plus 1 is 2, so this is root over 2, which is here. Okay. When F increases, F upon F is H increases, and therefore AF upon this whole factor decreases. So AF, AV decreases. Clear? When F tends to infinity, this term tends to 0. So the frequency response curve of Butterworth's second order low pass filter is shown in the figure below. Here. See here, when the frequency is 0, the gain is AF. As frequency increases, the gain starts falling, and when F equal to FH, the frequency is equal to FH, where FH is 1 upon 2 pi RC. Gain falls to AV upon root 2. So this is your upper cutoff frequency. The slope of this fall is minus 40 decibel per decade. Clear? So this is the frequency response curve of the Butterworth second order low pass filter. So in this lecture, we have determined the upper cutoff frequency of the Butterworth second order low pass filter. Also, we have calculated what will be the gain of the Butterworth second order filter. The graph is shown in the figure here. I assume you like this presentation. यदि आपको मेरा यह प्रेजेंटेशन अच्छा लगा हो तो इसे लाइक करें, शेयर करें और मेरे चैनल को सब्सक्राइब करें. So thank you for watching. See you next time with some other topic of interest. Till then, goodbye.